Hi, Tom the Professor here. It's time for another problem. Let's get started. The problem for today's episode comes from the sound chapter, and it also will illustrate why there's a delay to an echo or a delay between when you see the lightning and hear the thunder. Get those in the right order. I'll have the text up on the screen here and we will get started. We start with what do we know? Maggie's stone is going to fall a distance of 122.5 meters. And after the stone hits the bottom, it will take time for the sound to come back up to the top so that she can hear it. What we want to find is how much is the total time from when she releases to when she hears the stone fall. Now, in the possible solution, we will have to include the time of both the fall of the stone into the shaft, and we will also have to include the time for the sound to travel back after it makes the noise at the bottom. We relate distance and time with the one kinematic equation for distance. So let's calculate our fall time first using that equation. Distance is the initial speed times time plus half the acceleration times the time squared. Now in this case, she's going to release the stone from rest, so we can zero out that first term on the right hand side of the equation because the velocity will be 0. So 0 times time is still going to be 0. Solve that equation for time squared, and we get twice the distance over the acceleration, and we know all of those numbers, so we can calculate the time it will take to fall. Stick in the 122.5 meters, multiply by 2, divide by 9.8 meters per second each second, and we get a time for the fall of 5 seconds. Right? Keep track of that time. We don't want to lose it. We're going to need it here in a moment. Now, in order to calculate the time it takes for the sound to get back, we're still relating time and distance, so we're still going to use that same equation to start with. But in the second case, speed of sound in air is a constant, depending on the pressure and temperature of the air. But the sound does not accelerate through the air. So we can zero out the second term, because the acceleration is 0, so half of 0 is still 0. Time squared times 0 is still 0, so we're just left with distance is speed times time. Let's solve that for time, distance over speed, and then we'll take the 122.5 meters and divide it for the speed of sound in air, which is 343 meters per second. And we get a time of an additional 0.36 seconds for the sound to travel from the bottom of the shaft back up to the top. In order to get the total time, we simply add those two times together. For a time of 5.36 seconds after she drops the stone, she will hear the sound of it hitting the bottom. That's all there is to this particular problem. We used one equation basically, solved it a couple different ways, and we're able to get the time for the fall and for the sound to echo back essentially. If you liked this problem, make sure you like and subscribe to help support the channel. There's also merch you can check out. Give me some financial stability, hopefully, one of these days. The merch all goes towards paying for the channel, the website, the blog, all that fun stuff that I need to make these fabulous videos. If you want to send me a message, hit me up on the social medias at Tom Teaches Phys. And check out the blog at tomteacheспhysics.com, where I write a bunch of stuff about teaching physics, learning physics, what we should be teaching physics, what we should be learning in physics, and all that other fun stuff, all the other crazy ideas I happen to come up with in the particular day that I'm writing. Thank you for joining me, and I will see you next time.